I'm going to try something new today, and that is doing the recording through WebEx and just see how it goes. That way I can share multiple screens and things like that. So we're heading into chapter 16 now, which is all about redox reactions. So first I'd like you to get out your books and write down the heading chapter 16 redox reactions. We're still going to have the legend for icons, but I'm going to tell you also verbally what I'd like you to do. So here are is the agenda for the next 4 lessons. The first one, this lesson, is all about key terms and concepts. So introduction to redox. Oxidation numbers will be lesson 2. Writing out complex redox reactions, lesson 3, and using the electrochemical series is lesson 4. So I'm going to film 4 separate videos for this. Starting off, I would have loved to do this as a class discussion, but you might have seen this before and you might be thinking what it is. And you might have the word oxidation floating around in your head. And that's what's happening to this apple. It's being oxidized, and this is pretty much what redox will be all about. Again, what's happening to this bike? You might have heard the word oxidizing or rusting, and rusting is really when we turn iron into iron oxide. So you get that addition of oxygen. And, you know, apples, we can keep them fresher for longer by keeping them in a can. And you might be thinking, because it's actually reducing the amount of oxygen that's interacting with those apples and being able to react with it. So reducing the rate of oxidation by keeping it in a can. Here are some reactions, and you don't have to write this out. As you can see, there's no taking notes icon. I just want you to be aware of what type of reactions these are. And I can use the text here, which is really good. These are reactions that we've looked at before. Some we've looked at, some we haven't. So the first one you can see is an acid-base reaction because you have a hydrogen ion which is being transferred from the acid to the base. The next two are actually new. The next one is actually a new reaction called a redox reaction. You haven't seen that before. The next one, there's actually a mistake there. This is called a precipitation reaction, and you will have seen that one before. The next one, you can see the transfer of a hydrogen ion, so it's actually acid base. The next one, you can see you're forming precipitates, so it's a precipitation, but it's actually the ionic equation because you've separated the cation and the anion. So ionic precipitation. The next one down, you've got a precipitation reaction as well. And then you can see that this would definitely be acid base. And this is a new type of reaction, and it's called redox. And then finally, we've got an acid-base reaction here. So they're the types of reactions. You will become much more familiar with the redox ones as we move through. Now, why is it called oxidation? Again, you don't need to write any of this down. But in the past, they called this oxidation of iron and this reduction of iron. And as you can actually see, in oxidation, the iron is gaining oxygen. So you look at the products, it's got oxygen added to it, and the reactant has no oxygen. So it makes sense that they'd call that oxidation. They called this reduction, and as you can see, the opposite's happening. the iron is losing the oxygen. Why did they call it reduction? It's because through this process, you actually lose mass. So they were taking out iron ore, which is iron oxide, and they were smelting it to remove the oxygen, and they saw that you get a loss of mass. But then we sort of started getting a few difficulties because you started getting very, very similar reactions occurring, but with elements other than oxygen, you know, so they'd have iron plus chlorine and producing, let's just say it's iron 2, so FeCl2. So they'd call this chlorination, and then they'd call adding sulfur sulfonation, and it got a bit messy. So they needed a different definition, and you may see here, you may have already picked up that you're actually changing the charge of the reactants. So if I show you with the chlorine one as an example, you start off with no charge in iron, metal, and then you move to iron in the 2+ state. We call that oxidation state. And you can see that that change in charge must mean that there's something to do with electrons. So we get to our important definitions of redox. So you might want to write the subheadings. I've got some board notes that I'm going to be going through, which are the essential things that you need to know for these redox reactions. So I want you to have the heading, Chapter 16, Redox Reactions, as I've said before. Now, the subheading would be Redox Reactions, Key Terms and Concepts. Remember how I said that that's for Lesson 1. And here are the essential questions. So we're actually just going to answer these questions. I would do something like this on the board anyway. So what's an example of a redox reaction? As you saw, I had a little video up here, and I'm going to show you this example now. Okay. So without too much noise, here is an example of a redox reaction. You've got copper sulfate is the blue solution, and you've got zinc, and you can see that the zinc is darkening. And over time, the zinc will actually get a coating, a red coating over it, which comes out on camera looking black. I'm just skipping forward, but that's actually pure copper, okay? And you can see that the color of the solution is not blue anymore, and the blue is really the copper 2+. So this is an example of a redox reaction, so oxidations occurring in there that doesn't involve oxygen. So what's an example? I'll give you that example that we just put out before, that video was. So it was pure zinc solid. We added copper sulfate aqueous, and we produced zinc sulfate aqueous and copper solid. And I'm actually going to remove the sulfate because in redox reactions we write ionic equations, which means that the spectators need to be removed. So it makes it a lot easier to analyze. So I'd like you to get this down as an example. And here is, you can quite clearly see that you have changes in charge there. So what is an oxidation reaction? Well, on the PowerPoint, we saw that when iron is oxidized, it goes from a 0 to a positive. So it's actually becoming positive. So it's actually losing electrons. So oxidation refers to the loss of electrons. And reduction refers to the gain of electrons. What are redox reactions? Well, they are simply the transfer of electrons. Okay, so once you get that transfer of electrons, and you can see here that the zinc is losing electrons. So in this example, the zinc is losing electrons, so it's being oxidized. And the copper is gaining electrons. The copper 2+ is gaining electrons. So it's being reduced. Okay, so that's our first lot of definitions. How can you remember all of this? There's actually a nice little mnemonic that I remember from high school called oil rig, and that is oxidation is loss of electrons and reduction is gain of electrons. And that's what you can use to remember oil rig. So what are the steps in writing out these reactions? I've got the steps here. You can get them down at your own pace. So the steps in writing these equations, hopefully I can fit it all on the page just in case you want to press pause. I will get rid of these spaces here so it fits all on the same page. But first of all, you're balancing all of the atoms in the half equation, except for hydrogen and oxygen. Then you're balancing oxygen by adding water. Then you're balancing hydrogen by adding H+. So I'm sure you'll be able to read that and get those steps down. They're really important. And they're the same steps that you'll use in year 12. So let's have a look at an example, because you really won't be able to, oops, there's a step 7 there, cancel out species that appear on both sides. You really won't be able to understand it until I do an example. So we're going to do 2 examples here. First of all, we are going to write out the full or the overall and half equations for that top reaction and the overall and half equations for the bottom reaction. So let's start off with the top one. And first of all, part A asks us for the oxidation one. Okay, so we're going to consult these steps. All right, first of all, what is oxidized? Well, you've got to look at loss of electrons, right? So iron goes from 2+ to 3+, meaning that it's losing electrons because it's becoming more positive. So step 1 just says balance all the atoms except for oxygen and hydrogen. Okay, let's do that. So I'm going to copy those. I'm going to paste them under the half oxidation one. And I'm just going to simply have an arrow in between. The reason they write them out as half equations, so they're separating the reduction and oxidation, is because it makes it easier to do an overall. So we've done that, we've balanced because there's one ion on each side. Now we balance the oxygen atoms by adding water. Well, there's no oxygen atoms. So you skip that step. Balance the hydrogen atoms by adding H+. There's no hydrogen atoms, so you can skip that step. And really here, like, sorry, where I said the subheadings before, the complex redox reactions, that's what we're going to get into in lesson 4. But I wanted to give you all the steps now. Now, this is the really important one, step 4, balance the charges by adding electrons. So what we're going to go ahead and do is we're going to add electrons, and you always add electrons to the more positive side because electrons are negative. So I'm going to add electrons here, and electrons is shown with an E and a superscript negative because they're negatively charged, and they have a 1 negative charge. So we have a 2 positive charge on the left-hand side, and we have a 3 positive charge on the right-hand side. So we need to make sure that they're equal. Okay, so we add an electron, which is 1 negative. So that means that on the right-hand side, we have a 2 plus charge. So we've got positive 3 minus 1 is positive 2. Positive 2 and positive 2, the charge is conserved. Now, this is when you're writing the overall equations, so we are going to do that later, but let's just write out our other half equation. So I'm going to have the hydrogen on the product side for reduction, okay, and the reactant side, I'm going to have H plus. And you can see here that in this half equation, it's already balanced. So adding H plus, originally it would have been like this, and we would have to put a 2 to balance the number of atoms on each side. Now I need to balance for charge. If you look through the steps, none of the other steps actually relate to this half equation. So I'm going to add electrons to the more positive side. There's a 2 plus charge here. There's a 0 charge there. So I'm going to need to add it to the left-hand side. And I'm going to add 2 electrons. Okay, so 2 electrons plus 2 positives makes 0 and 0 on the right-hand side. Now we're going to do the overall. The overall, it says, so I just want to make this really clear. This is losing 1 electron, the iron. The hydrogen is gaining 2 electrons, which means that, you know, there's an imbalance here. We need to make sure that the hydrogen is gaining the electrons that the iron is losing. Otherwise, where is it getting these electrons from? Thin air. So when we write the overall equation, we multiply the half equations so that the number of electrons lost equals the number gained. So I'm going to do that now. I'm just going to do it in the steps, even though you may be able to skip this intermediate step. Okay, so the number of electrons lost is 1, number of electrons gained is 2, that's not right. So I'm going to multiply this half equation by 2. Basically, you're just trying to find their common multiple, and all that involves is putting a 2 in front of each species. Here you go. And then you're simply adding them together. So it's literally the top plus the bottom. And the way you add those together is you just put all of the reactants on one side. So I'm going to just copy and paste those reactants here. And then you put all of the products on the other side. So I'm going to do that. Just give me a minute. Just don't want that to be superscript. And then I want these as well. Okay, and I just want to have a plus here. All right, nearly there. And that looks like a good overall equation. Now we're going to head to step 7, which basically says cross out species that appear on both sides, and that's the electrons. So you can see that the electrons come in, so 2 come in and 2 go out, which means that there is an overall of 0 electrons, net 0. So we cross them out, and here is the balanced overall equation. Okay, and what are the conjugate redox pairs? So here is another important key terminology. What are the conjugate redox pairs? Well, the conjugate acid-base pairs differed by the H+. So the conjugate redox pairs actually just differ by electrons. So we've got two conjugate pairs here. We've got H plus and H2. So you would just write it out like this. And the other one is H2 and, oops, sorry, Fe3 plus and Fe2 plus. And you don't need to carry the 2 there, but I can't see an issue if you write the 2 there. So this is one pair and this is that second pair. Okay. And let's do the second equation now. The second example. So the second example, I'll just paste it here so I can see it. When a strip of copper wire is suspended in solution of silver nitrate, long crystals of silver metal can be observed. So that tells me that silver nitrate is AgNO3. You have to know what that is. Okay. It is suspended in a solution, copper wire. Copper wire is copper solid. Long crystals of silver can be seen, so that's now silver solid, and copper 2+ ions are produced. I'm going to go ahead and remove the spectator. So the spectator will be the nitrate because they have no information about the product, meaning that it won't participate in the reaction. So let's write out the half equations. First of all, you can see that, whoops. Yep. First of all, you can see that the silver is actually going down in charge, meaning that it's gaining electrons. So the silver is being reduced. And the copper is losing electrons, so it must be being oxidized. Okay. Yeah. So let's balance. Now there's no hydrogen or oxygen, so all I'm going to do is balance for electrons and then combine them by multiplying each half equation so that they fit together. So 1 plus on the left-hand side, 0 on the right. So I need to add my 1 electron here to the right-hand side. Note that electrons don't have states. And in the other half equation, I'm going to add 2 electrons to the product side. Okay. And overall, okay, I'm going to basically multiply the top half equation by 2, and I'm going to cancel out my electrons. So I'm going to end up with copper solid plus 2 silver positives produces, and we need to make sure we have our aqueous in there, so states are really important. All of your ions will be aqueous. And notice that they have charges because they're without the anion. And plus silver solid. Okay. Now, the final part of this lesson, as you can see, we're heading into lesson 2 now. So the final part of this lesson is basically looking at a little bit more terminology, which is annoying. Oxidants and reductants, or oxidizing and reducing agents. Now, from the name, it kind of makes you think that a reducing agent is something that forces reduction. And the way I usually just draw this on the board, it's pretty strange, is thinking about the words murderer and murdered. So the person who is the murderer is actually doing the killing. and the person who is murdered is actually the victim. So they're supposed to be crosses in the eyes. So here is the murderer. Okay, and here is the murdered. So in that same idea, if I have a look at copper 2 plus reacting with zinc in that first equation and producing copper solid, the zinc is giving electrons to the copper 2 plus. You can think about them like little bullets. So the zinc is actually causing reduction. So the zinc is the reducing agent / reductant, but the zinc is being oxidized. It's very backwards. If we were at school, I would do a little ball game to really hone this idea. But at the same token, the copper is being reduced because it's gaining electrons, but it is the oxidant. Because it is causing oxidation. So if we have a look back through, so you might want to get that down as an example, but if we have a look back through at the essential questions, they were just asking what is an oxidant / oxidizing agent. So as a definition, an oxidizing agent causes oxidation by taking electrons and is itself reduced. Whereas a reducing agent, causes reduction by losing electrons and is itself oxidized. So that's it for the terminology and intro to redox. Feel free to pop into WebEx if you need help with that. I'll see if I can actually stop this recording. Do you want to stop the recording? If you stop the recording and then restart at a later stage, a separate recording file will be created.